Thank you. Thank you, Sergey. And thank you. I did not know that we were going to be twinsies tonight. And we got to get a twinsy picture at the end.
Who can guess what?
Does anybody know what this is from? Yes. So, all right. Well, here, I should probably. So, welcome to Happy Browser, Happy User. My name is Katie Seiler-Miller. I'm a staff software engineer on the Frontend Systems team at Etsy. I've done a couple of other cool things. I worked on the Design Systems Handbook, which is a free ebook about building your own design systems. You can go to that bit.ly link to go and look at it. And I made this ridiculous website called Oh Shit Git, which this t-shirt is from. You can order these t-shirts. You know, I probably should have added the link, but I have a more important link on the slide, which is I was very lucky to get to collaborate with Julia Evans, who makes the Wizard zines, and we made an Oh Shit Git zine. If you go to that link, you can order one to purchase. It also comes bundled with the free Dang It Git swear-free version. So, and there's also dangitgit.com you can go to. So a lot of folks asked for that, saying, "Oh, I teach a class and I want to share this, but I can't use the swears, or my corporate URLs blocker blocks your website." So, and and if you go follow Oh Shit Git on Twitter, you can find links to buy your own amazing Oh Shit Git t-shirts. There's stickers up on the sticker table. So, yeah, anyways. Cool. So, if any of you have been in the performance community for any amount of time, you've probably heard this phrase thrown around a lot. Performance is UX. Now, the idea behind this is pretty simple. I mean, better performing sites provide a better user experience for our users. We all kind of know on the surface what this means, but really in this talk, what I want to do is dig deep into what does performance is UX actually mean. So like UX, again, we know what UX is. UX is we build our websites for people. We want to have a better experience for our users. We want them to come and use our site. We want them to buy our products. We want them to read our blogs or use our service. You know, the great thing about UX is we kind of already know what makes users happy. We're users ourselves. We understand what it means to have a good performing web experience. It means that we get a fast loading content on the website. And that's something I think is really important, is that people talk about fast loading all the time, but what they're really talking about is fast rendering. They want to see content on the screen as quickly as humanly possible so that they can get the information that's most important to them. They also want to have instant feedback when they click or they tap or they use a keyboard to interact with our websites. We've all been in that situation where you load up the site, you tap the button, and nothing happens, and you go tap, 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 and still nothing happens, and then like 3 seconds later, you get a million pop-ups open and close, and everything is all like janked up because you couldn't see that you actually tapped the button and something was happening. Another thing that we want to see as users is smooth animation. So when you scroll on your website, on a phone especially, you know, we've all experienced that like stuttering, janking animation where it goes, nobody likes that. And another thing that I'll throw in there that's a bonus is users really don't want you to use up all of their mobile data. Mobile plans are pretty expensive, especially in developing countries. There's been this concept thrown around of the next billion users. So those are folks in developing nations who they mostly access the internet through their phones. They don't have home internet plans, so the cost of data is really, really important to those users. So as good citizens of the net, we don't want to use up our users' mobile data. Okay, so that's UX. Now what does performance mean? Well, performance is this really big, huge umbrella topic. It covers a ton of different things. DNS servers, prefetching, preloading, image compression, the purple pattern, the rail pattern, frame rate, layout thrashing. Like, these are all terms that you hear thrown around. And if you're just getting started out, I was right where you are just a couple years ago, and it's confusing as heck. Like, there's a lot to learn and a lot to know about. 2 years ago, when my team at Etsy was given the task of making our mobile listing page load faster, we kind of came in and we really didn't have any idea what to do. And it's because the topic is so broad. And then we really dove into performance and like trying to think about, how do we make this better? How do we teach other people how to go out and make sites better? And we kept running into the same problem, which is, in order to teach somebody about performance, you have to first teach them about how browsers work, right? Because all the different things that we talk about in the performance community, the thing that ties them all together is the browser. So I had this epiphany that really, we build websites for browsers. We don't build websites for people. Well, no, we do. We build our websites for people. Don't forget about the people. But before the people can see anything, before the people can do anything, it all has to go through the browser first. So really, when we're talking about performance, we're talking about writing our code in such a way that it's easier for the browser to do its job. We want to make the browser happy. So how do we do that? Well, I don't know about anybody else in this room. Like, did anybody go to a boot camp and learn how browsers work? Did you learn in college? Did you get trained on the job? No. This is a huge failure for web development as a whole. We fail to teach people about the most fundamental thing for every piece of code that we write for our websites, which is how the heck it actually appears on a browser, right? So we're gonna learn that. We're gonna learn how do browsers work. And in order to understand what makes browsers happy, first we have to know what makes our browsers sad. Oh, poor browser. My husband drew these little cartoons for me. I was like, can you draw a browser that's really happy and then a browser that's really bummed out? And he was like, okay, Katie, whatever. All right, so the two major problems that we can kind of take all of the performance tips and tricks and things that we learn about, we can bucket into these two things. We're trying to work around network latency. So this is a pretty easy concept to grok. Network latency means, hey, it actually takes time to send bits over the air and into wires and back out again. And then the other kind of giant bucket that a lot of things fall into is the mostly single-threaded nature of web browsers, all right? But what does that mean? So I apologize, we're gonna talk about some real boring computer stuff for a second. So computers have these things called hardware. Oh, wow, no. The parts of the computer hardware that we are most interested in are the CPU, which is the brain of the computer, the GPU, which is a graphics processing unit, which is what paints pixels onto a screen, and then a network controller. So that's a card that either connects to a wired network or connects to a Wi-Fi. And then layered on top of that hardware is the operating system. Now, the operating system has the kernel. You see that's a ear of corn? I don't know. I was like, how do I represent the kernel? I don't know. It's a corn. So that's the main part of the operating system. The kernel manages memory, all of your hardware usage, data storage, all of that. And the way that the kernel exposes the underlying hardware complexity of the computer to applications is through processes, which are little allocated blocks of memory for your program to use. And then within processes, there's 0 to many threads. So a thread is basically, you can think of it as a place that executes code. And then finally, there's also a networking layer in the operating system. And then layered on top of that is our application. So applications can use multiple processes. And again, each of the processes that it could have 1, 0, multiple threads inside of it. And the way that browsers work is that all of the browsers are slightly different architecture, but basically all of them has one process that is like an orchestrator that takes care of everything else. And then there's generally a process that's dedicated to rendering and graphics. And then depending on which browser you use, there's one process per tab. There's actually in Chrome, there's a separate process per iframe as well. And then other browsers, there might be 3 or 4 tabs that share a process. And then within that browser tab process, there's generally one thread that does just about everything. And as we progress, you're going to see all of the different things that our poor, overworked main thread works. This is my good joke. The browser's main thread is like a working mom. It does everything. See, I'm a working mom, so yes, thank you. My colleague is clapping for me, so. All right, so to better understand how browsers work, we're going to take that classic computer science interview question of what happens when you type something into your URL bar, and we're going to get really in depth into it. So we're all going to be able to ace that interview question after that. I hope everyone goes out and gets a new job thanks to me. You're welcome. Except for everyone who works at Etsy. No, you're not. So really there's 4 main phases to how the browser works. The first phase is navigation. So that's everything from when the user types the URL into the browser to connecting to the remote server and then getting data back. And then once we get our data back, we parse it, which means reading through all of the text in the HTML, CSS, and JavaScript files, and then turning that into something that the computer can understand. And then the most important part of all, which is rendering, which is taking all of that bytecode and all of that stuff that the computer understands and turning it into a picture on a screen. And then finally, we can't forget about the super important final phase, which is the user actually interacting with your website. All right, so navigation. So navigation starts as soon as the user types a URL into their browser. So I actually don't go to this website. I bought it, though. I own this website. It's called mindblowncat.com. It's a tribute to the absolute most amazing animated GIF of a cat ever of all time. And by the end of this presentation, we will get to see that GIF. So don't go to the website and ruin the big reveal at the end, okay? All right. And also, it makes it, like, I hope at the end you're like, whoa, computers, mind blown, All right. So navigation, this whole entire phase is completely opaque to our users. They have no idea that this is happening. All they know is that there's a little spinner in their URL bar. So we want to get this over with as soon as we can. But there's a lot of stuff that's going to try to prevent us from doing that. Now, the first thing is that every single request that we make to the internet from something like a mobile phone, it first needs to go through the cellular network, which then passes off your request to like the real internet. So every single time we go off to request data, it's at least 2 hops. Now we're going to type our URL into our URL bar, and the first thing our browser does is what's called DNS lookup. So DNS lookup is where it takes the text of www.mindblowncat.com and translates that into an IP address, which the computer can use to talk to another computer. The whole DNS process is actually really, really complicated. I'm not going to go into it, but just basically know that there's like several different layers of computers involved in every single DNS request, especially when you go to a website for the very first time. Now, once that's set up, we know where the server is. Ta-da, we found the server. Our browser goes and makes what's called a TCP 3-way handshake. So this is like a way for the computer to say, hey, server, I'm here, and the server responds with ACK, and so that's 3 hops back and forth. Next, because again, we are really amazing citizens of the internet, we want everyone to use a secure connection so that their data is safer. We have to go and make a SSL connection. Now this is a 5-way handshake of sending information back and forth. So now we are up to 11 round trips between our web browser and the server, and we don't have a single piece of data that we can do anything with yet. The way that we do that is we make our 12th request, which is for HTTP GET request. Now our server gets this request, and it goes off and it does all of its server stuff. And then it puts together some package of HTML and returns it back to our phone. And that is, when we're talking about performance timing, that's called our time to first byte, or TTFB. All right, whew, we finally got some data. Awesome, right? Now, has anybody ever heard of this thing called the first 14 kilobyte rule? Yeah, awesome. All right, so the first 14 kilobyte rule is based on this cool thing about the way that the TCP algorithm works. There we go, sorry. Too many clicks. It's called TCP slow start. So what it means is that the browser initially sends 10, or the Yeah, the server initially sends 10 packets of data over to your browser, which represents approximately 14 kilobytes of data. Your browser accepts the packets and sends back a receipt saying, yes, I got that information. The server will then send back double the amount of information as long as everything is okay. So it'll send approximately 29 kilobytes the next round trip. And this will continue until the algorithm reaches a point where the data is not coming through any faster or better, and then it'll kind of plateau out. You know, the first 14 kilobyte rule is basically like, we want to stuff as much of our important content into that initial request as we can, because that means that the server doesn't have to do yet another round trip in order to get more data. So this is why the first 14 kilobyte rule exists. All right, this all happens in a couple hundred milliseconds. Isn't that bananas? Like, how does this happen? I don't know. Computers are amazing. But the really sad thing about this is, like, what do we have control over in this diagram? Not a lot, right? We mostly have control over this server stuff. So that's what we need to work on if we want to improve our navigation time, is we want to reduce the amount of time that our server takes to put together and send back a request. And the way that we do that is we cache the hell out of everything that we can, and we use a CDN like Fastly, which will take all of our static files and hold them in servers all around the world, so that when our users in Bangalore make a request for a file, they don't have to route their request all the way to New York City in order to get data back. Another thing that we can do to improve our navigation time is to send smaller files, and then we have to do fewer of those round trips. And the way that we can make our files smaller is by using things like compression, gzipping all of our assets, tree shaking and code splitting to help us reduce the amount of JavaScript in particular. I don't know if anyone here has read, Adi Osmani gave a really amazing presentation and wrote a really amazing talk about, I think it's called The State of JavaScript 2019. I have a slide at the end with a link to a bunch of resources, and that's in there, where he talks about why JavaScript is probably the biggest blocker as far as performance. So take care of your JavaScript. Send as little of it as you can. Again, the first 14 kilobyte rule, we can use that to our advantage. And then we can use a whole bunch of really advanced performance things like preloading, prefetching, resource hints, and HTTP2, which honestly, there are multiple talks about each one of those in isolation. I don't really have time to go into all of them in detail, but again, in the links at the end of the presentation, there'll be some resources so you can go learn more about those buzzwords. Cool, so our navigation is done. It is time for us to parse. Now, I hope everybody likes trees, because basically this entire thing is about constructing trees, which is a data structure of a node that has a bunch of children, and those children have children, if any of you didn't really study data structures. So our goal for the parsing phase is that we want to construct the DOM and the CSS as quickly as humanly possible, because that's what the browser needs in order to actually show something on screen. Because again, your users don't care about this phase. They want to see something on screen. So we want to get this over with as soon as we can. So for the rest of this, we're going to talk about basically getting really super in-depth into what happens with this set of markup. Now this is really simple. You can see we have a very small document. We have a title, we have an external style sheet, we have a link out to a JavaScript file, and then we have our amazing, awesome, most best cat GIF ever of all time in the body. But a lot of this is actually a really bad idea. And we're going to find out why this is a really bad idea. So the first thing we want to start on is building the DOM, or the document object model. Now the DOM is like the browser's internal representation of the HTML markup, and the DOM is also what the browser uses to expose manipulations of the markup to the JavaScript API. So it's like a really important fundamental data structure that the browser needs. So the way that DOM parsing works is it uses what's called a lexical parser, which takes all of the characters in the file and then goes through them one by one and decides when it's hit an opening HTML tag, a closing HTML tag. It parses out everything in between those two little pointy brackets, and then decides, okay, this is an HTML node. Haha, yes, we have our first DOM node. Easy, right? So we're going to continue on our little thread journey, but modern browsers are amazing, and they want to help us. So the next thing that'll actually happen is something called a preload scanner or a look-ahead scanner or a preload parser. I've heard it with a bunch of different names. I think every browser calls it something different. It's going to go off and try to find all of our external links that exist in our markup and go and make an early request for those. So they're trying to help us out. So one thing to note about this is, like, if you have JavaScript that is inserting images, it means that the parser can't find it right away. Sometimes that might be what you want if you want to do lazy loading, but sometimes that might not be what you want. So you have to be careful about how you reference your external resources directly in your markup, because the browser is going to try to help you, and you want to help the browser. Next, we go and we parse the DOM some more. We create our head element, and then the title element is created as a child. And then we get to this style tag, but we've already gone off and made a request for that, so it keeps moving. And it hits our script tag. And oh, we're stuck. We can't go any farther. And why is that? Well, it's because JavaScript is render blocking when you include it without the defer or the async attributes. So don't worry if you don't know what defer and async are. I'm going to talk about them shortly. All right, so we have to wait for our JavaScript. But before we can even start looking at our JavaScript, we have to wait for our CSS. So CSS blocks JavaScript. I don't know if any of you have heard the adage, styles in the head, script at the bottom. This is why. Because in order to actually start parsing JavaScript, the browser is going to stop and wait, because there could be stuff in your JavaScript that's trying to access style properties. So they don't want to have like a weird race condition. So we have to stop and wait for our CSS. So, here comes our CSS file back over the network. So let's start parsing our CSS OM, or CSS object model. And again, this is another tree representation where there's a parser that goes through our CSS and takes every individual character and tries to figure out what is a style declaration, what all the properties are. And then it takes that information and creates a tree. You can see everything is nested. So like we had that .border image. So the way that it represents in the tree that relationship of a child selector is it creates the image style like declaration as a child of the .border style declaration. Why does that matter? Well, when you think about how we want to be able to quickly parse through the CSS OM, the deeper that you nest your CSS selectors, the deeper you're also going to make the nesting in this tree, which means that it's going to take the browser even longer to parse through and find those leaf nodes. So the way to make CSS OM better for the browser is to avoid deeply nested selectors and try to keep things as flat as you can. Cool, all right, so let's go back to the DOM, Marty. All right, so our CSS OM is done, and while we were off waiting for that, our JavaScript file came back. Woohoo! So now we can move on to parsing and executing our JavaScript. All right, so JavaScript gets parsed into what's called an abstract syntax tree. I have to say that very slowly because it's very hard to say. AST is much easier. So what is an AST? It's another tree. Surprise. I hope you like trees, because there's still more trees to come. Anyways, JavaScript ASTs are completely and utterly bonkers. Basically, I'm gonna just go through this animation really quickly and not really talk about it too much because it's bananas. Basically, what you should do is just understand that it does that same lexical parsing where it goes through and it takes every single character in the JavaScript and then converts that into an object that represents what, if this is a function, if this is a variable, are we calling a function versus defining a function? What is the identifier for this variable? This is just bananas, but what you can do is you can go to this astexplorer.net and you can just start typing JavaScript into the like text file, and it'll show you the tree of everything. So suffice to say, ASTs are really cool. They're really interesting. You can make an AST for just about any programming language that you want. They're really powerful. but they're bananas. All right, so now that we have our AST, we're going to take all of that JavaScript and we're going to immediately compile and execute it. So this is a little bit different than with CSS, obviously. So the implementation details of how browsers actually interpret and execute JavaScript is pretty similar. There's a little bit of differences, but generally what happens is they take that AST and they send it into an interpreter. And what the interpreter does is it very quickly outputs something called bytecode. And now bytecode is what the computer understands and the computer can actually execute. However, bytecode executes kind of slowly. So in order to help us make our JavaScript go faster, what browser manufacturers have done is they then take that bytecode and they send it to one or more optimizing compilers. And what the optimizing compiler does is it takes a little bit longer, but what it outputs is optimized code, which then when we put it back on the main thread, it executes faster. So the browser manufacturers are trying to help us. There's a lot of really intricate detail about how to write your JavaScript and how to serve it and to help the optimizing compilers do their job better. I'm not going to tell you any of that because I don't understand it myself. But again, in the resources at the end of the talk, there's links to talks by the folks who worked on the V8 JavaScript engine, which is like the new hotness fast JavaScript engine. So now our JavaScript has been parsed and compiled, and we're going to execute this bad idea. So as you can see, we have our function, bad idea. We declare a variable called cat, which we call document get element by ID cat, which is the ID of our awesome animated GIF. And then we want to change the source of that to some other URL. And then we call our function bad idea, and we get an uncaught type error. I don't know, this is like frustrating, but why do we have an uncaught type error? What it's saying is it cannot set the property src of null. So what it's saying is that that variable cat is actually null. Why is the variable cat null? Any ideas? Why? The cat element doesn't exist in the DOM yet. Yeah, this is what our DOM looks like right now. We don't have a body yet. There's no cats in here. So this is why, if any of you have ever written anything in jQuery, there's that document.ready handler. And what that does is it says, wait, hold on a second. I know you're going to execute this JS when the DOM isn't complete. Hold up. Don't actually run this and try to grab stuff out of the DOM until the entire DOM exists. Wait for that DOM ready, or it's actually the DOM interactive event, which we'll talk about shortly. You know, most modern frameworks take care of this for you. You don't have to think about it. But if you ever want to write your own like vanilla JavaScript and you run into these like really annoying, baffling errors, this is why. It's because your JavaScript, when we load it in the head like this, the DOM doesn't totally exist. All right, so let's go back to the DOM again. Thank you. Nobody ever laughs at the Back to the Future. I mean, come on. That's a funny movie, people know. All right, so when last we left our DOM, we were blocked, but we just parsed and executed all of our JavaScript, so we are unblocked. So we can continue to go through our HTML and create our tree of elements. One thing I want to point out is that all of the text inside of an element gets its own node. And if we had something like comments, comments also get their own node in the DOM tree. And I don't know if this has a light, but I don't know if I can point out here. So see this P here is a cat. I didn't close that P tag. And that's totally valid in the HTML4 and HTML5 specs. The browser parser is like super fault tolerant, and it's going to allow you to do stuff like this. And it will try to figure out, okay, where does this P tag end? And it'll make its best guess for you when it generates this tree, which generally can be pretty cool. Like generally it works out, it's fine. However, it can go horribly wrong. This was a tweet by Bruce Lawson. He works for Smashing Magazine. They found out that they had a misnested span that made it look like their entire ebook was crossed out because they didn't test it in the iPhone Reader app. Because like who would test in the iPhone Reader app? I mean, has anybody here ever tested in the iPhone? No. Yeah, if you raised your hand, I would call you a liar. But not every parser that parses HTML is forgiving or works the same way as browsers. So this is why, even though the HTML spec is really awesome and it's fault tolerant, just nest your HTML properly. It's going to make the browser's job way easier. It won't have to guess for you, because it'll guess wrong, because it's a computer. It's not a person. It doesn't know what you want. All right, so we're done with parsing. Deep breath. But we can make that better. That was terrible. I don't know if you know, but that was just terrible. Now remember what our goal was. Our goal was we wanted to get to the DOM and the CSS as fast as humanly possible. So the browser can then start helping us out and render stuff onto the screen. So this is what we did. If you start over from the left, you can see navigation start. There's the three threads. The main thread, our worker thread, which actually I kind of took a couple of different kinds of worker threads and like mushed them into one line. And then there's our network process. So you can see at navigation start, the network process requests the HTML. The HTML comes back, it gets passed to the main thread. That's our time to first byte measurement. And then you can see the main thread starts parsing our HTML. It passes the information off to the preload scanner, which then requests our CSS, our JS, and our image. And in the meanwhile, the DOM has to pause and wait for that CSS to come back. Because remember, we got to the script tag, and the script tag said, hold up, I need some CSS before I can do anything. So we had to sit around and wait, and then we parse the CSS, and then when we're done, our JavaScript comes back, but the JavaScript has to sit around and wait for the CSS to complete. And then once that's done, it can parse and execute all of that JavaScript, and then finally it can go back and create the actual body of the HTML, which is what we want in order to show something to the user. And then once all the HTML is complete, the browser fires that DOM interactive and then the DOM content loaded events. So how can we make this better? Well, remember what we said, we want to get stuff into that first 14 kilobytes. So our style sheet was pretty small, so let's just inline that in the head. So what does this do? So you can see we still kind of have the same initial request. We parse the HTML, it gets passed off to the preload scanner. But this time what happens is it gets to that block of CSS inline in the head, and it parses it immediately. Then all we have to do is just sit around and wait for that JavaScript to come back so we can parse and execute the JavaScript. And then we can go ahead and build the DOM. Now this is better, but we can still do even better than this. Before, remember, there was that sort of styles at the top, scripts at the bottom. So if we take our scripts, and you know what, our scripts are pretty small too, so let's just inline those, because we don't need to make that extra HTTP request. So now this looks a lot better. We parse our HTML, parse CSS. We finish parsing the rest of the HTML immediately. We fire that DOM interactive, which means that the DOM is completely built in memory. And then we get to that script at the bottom, and we can parse and execute that, and then DOM content loaded fires at the end. So as soon as we get to that DOM interactive, the browser can start to put something together to show on screen to our users. So this is way better. But what if your JavaScript is actually a really big file and you can't inline it in your document, because that would just be bananas? What you can do is you can use the async attribute on your script tag up there. And what async does is it tells the browser you can go off and request this JavaScript, and then I promise that I'm not going to modify the DOM in my JS. So you can go ahead and continue parsing the HTML while we wait for this JavaScript to come back. So you can see that reflected in our timeline. We parse our HTML, we parse our CSS, we continue to parse our HTML, and then we pause when that JavaScript file comes back. And because the browser is single-threaded, we have to parse and execute it. We pause DOM construction, parse and execute it, finish constructing the DOM, we fire our things. Now this looks bad, like this actually made things worse. So you're like, Katie, why are you telling me that I should be async loading my larger files? Well, when we have a giant JavaScript file, that changes the profile considerably. Because what happens is we say, keep on going, parse the rest of the DOM, and then whenever that file comes back, parse and execute it. So with a very small script, async doesn't make any sense at all. But with a very large script, async is going to be a huge boon to your users, because you're going to get all of that information that you need to show something on screen way faster. The other option that you have for like better script loading is defer. So the difference with defer is that it will wait when it gets that JavaScript until the end of DOM parsing before it tries to parse and execute it. And defer is really good if you have older scripts that maybe like they have to be loaded in a particular order, because defer will take the scripts in the order that they're defined in the DOM and will execute them in that order. We have this problem at Etsy where we have script files that rely on other script files. So we could defer them. We can't defer them for reasons that I can tell you about if you want to know later when I've had a couple drinks. Cool. All right. So let's check in with our poor working mom, the main thread. What is it doing? So it's parsing the HTML into the DOM. It's parsing CSS into the CSSOM. It's parsing JavaScript into an AST, and it's executing that JavaScript. Wow. All right. So let's move on. Now this is where the magic happens, rendering. We're finally going to get to see the best cat GIF ever of all time. I hope you're ready. It's going to be a while, though. I'm sorry. There's a lot more information. All right. So our goal for the rendering phase is that we want to do as little work as humanly possible. Renderers are lazy because rendering takes a lot of work. Now, the rendering pipeline is what we generally call this process. There's 4 different steps: style, layout, paint, and composite. And out of these 4 steps, layout and paint in the middle are particularly expensive, so we want to avoid doing them whenever we can. So let's dive in a little deeper. Style. What does it mean to style? This is where we take those 2 trees, the DOM and the CSSOM, and we mush them together to calculate the style of another tree. Wow, another tree. Happy little trees. So anyways, this is where the C in CSS and the silent, or S in CSS, cascade and specificity come into play. This is how the browser decides, okay, I've got this DOM tree and I've got this CSS-OM tree. How do they fit together? How do I decide what styles to apply to which nodes? And then it generates this new computed style out of it. And one thing to note that's going to come into play later, so don't forget, this is really, there's a quiz afterwards. Anything that has display none set doesn't end up in your calculated style tree. Visibility hidden, however, does. This is going to come back and bite us in the ass. So remember, display none doesn't end up in your computed style tree. All right, so next we're going to lay out our page. So what that means is we take that render tree that we just created and we make another tree. Although I'm kind of sick of trees, so we're going to show this a little more visually with squares. But just remember that the computer doesn't think of this as squares. It's just another tree of objects, where it basically takes all of these elements that we have and then decides what is the height and width of them. So first it starts with the viewport. And it says, oh, that's my root element, HTML element. It holds on to the size of that. And then it goes recursively through the tree and makes space for everything. As you can see, the H1 tag, it calculates the font height. So I'm not going to talk about this, but everyone should go and watch. Zach Leatherman talks a lot about font loading strategies. Font loading strategies are really important because if I was using a web font instead of a native font, and that web font took a long time to come back, the height of that high tag would actually change, and so the browser would have to recalculate. I'm not going to talk about it, but just know that font loading strategies are important to help make this process more smooth. All right, so then we insert the P tag and the text, and then we have our div with a border, and then we insert our image. And that GIF is massive. It's not back yet. So what the browser does is it's like, I guess I'll just leave a little space for it, and then there's like a default size, and i.e. it's 300 pixels wide. This is like a thing, I don't know. If you've ever had to do old IE, you've probably encountered the 300 pixel size bug with Flexbox and tables. Anyways, sorry, I was getting nostalgic there. All right, so next up is painting. Now this is where the browser takes all of that information that we just did by laying out our boxes our boxes in a tree, and then it quote unquote paints it to the screen. Now this is also, it's not actually painting anything, so this is like a really bad name. What it's doing is it's creating what's called a frame buffer. And a frame buffer is an array which has a bunch of child arrays, and each one represents a pixel location on screen. And then inside there's a RGB and A value, so it's the red, green, and blue values for that particular pixel on screen. The A value is opacity, so that subtly changes it. The browser can then take all of the data inside of this frame buffer and use that to actually show the pixels on screen to you. Why is this important? Well, pixels. There's a lot of fucking pixels in mobile phones. I have an iPhone X. It has 2.7 million pixels to render. 2.7 million items in that frame buffer array. Computers, oh my God. So painting's a lot of work. So this is why we don't want to paint unless we absolutely have to. So how can we do less work? Well, one of the ways that modern browsers try to reduce the amount of work they have to do is with layers. So these aren't necessarily the actual layers the browser would create. I just made them to like show you the concept. But it will slice the content up and put it on different layers. And then what it can do is in the next step of the render pipeline, it smushes the layers back together. Why does that matter? Well, if you're animating something on screen and it's in its own layer, then you can just move that thing around, and then you don't have to repaint the entire screen. You can repaint just pieces of the screen. So whenever possible, especially again if you're doing animations, you want to push your pixels into a new layer. There's a bunch of different ways to do that. They're not really important. Be careful though, because like with great power comes great responsibility. Layers are really expensive in memory, so you don't want to overdo it, but this can be a really good performance optimization. Because in our next step, compositing, the browser is going to smush these pixels back together to make our final bitmap using our new BFF, the GPU, or the graphics processing unit. GPUs didn't used to be super ubiquitous. It was like only for specialized gaming PCs. But nowadays, the computers that we all have in our pockets, if you have a higher end phone, it has a GPU in it. And the GPU is really, 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 really good at making lots and lots of little tiny calculations simultaneously and very fast. What is that really good for? Well, that's really good for shading things in a video game. It's really good for displaying things on screen. There's a couple of really good resources where you can learn some more about the GPU by Lynn Clark, who works for Mozilla. She is amazing and brilliant, and I did not understand the difference between GPU and CPU until she talked about it. So anyways, go read that. So what does the GPU do? Well, it uses math to take our two different layers. So each layer has its own frame buffer of positions of pixels on the screen, and the GPU uses math. So I don't know how many of you have actually used Photoshop and used blend modes for layers like lighten and darken and multiply. So those are basically mathematical functions where you pass in two different pixel values, one that's on top and one that's on the bottom, and then it uses math to spit back out a combined pixel value for those two layers combined with each other using the function that you want. There's CSS blend modes. Unikravitz talks about CSS blend modes a lot, so you can use this to do all kinds of really cool and funky things with your markup. All right, and then that GPU spits out our final frame buffer, which finally gets sent to the screen to display. Ta-da! We have something on screen. Oh, but we don't have that GIF yet because that was a really massive file. It's like almost a megabyte, so it takes a really long time. All right, so this is where we are in our process. We parsed our HTML, our CSS. We parsed and executed the JavaScript. We did some styling, did some layout, some paint, and then compositing happened off the main thread. It happened on the GPU as a separate thread, which we want to do more of that because the GPU is awesome. All right, so reflow. Has anybody heard of the term reflow before? Yeah. Reflow means that we have to redo one or more of those steps in our pipeline. And reflow makes the browser extremely sad. We do not want to reflow, but I just made the browser reflow. I apologize, browser. Why do we need to do that? Well, I didn't tell it how big that image was. When the image comes back, the browser has to recalculate the height of that div, so it has to re-layout everything on the screen. and then it has to repaint. Ta-da. Okay, and then and then it had to recomposite everything into one single layer with math. So we didn't have to do that, right? We didn't have to do those 3 extra steps all over again when our image came back over the wire. If we had simply given the image a height and a width, then the browser would have known how much space to leave for it, and then it would only have to repaint and recomposite. And again, compositing is okay. We can recomposite until our faces are blue. It's cool. But painting and layout are the expensive things. Now this is why, I don't know if anyone saw the announcement recently that Google Chrome shipped an update that they're gonna start calculating intrinsic image sizes better. But this is why that's so important, is because if the browser can figure out how big the image is, it can leave the proper amount of space for it, and then we don't have to reflow when the image actually comes back over the network. Cool, so let's check in our poor main thread. It's now doing 1, 2, 3, 4, 5, 6, 7 things. And we actually have something new coming that we're gonna task our poor main thread with. Ah, why do I keep hitting the wrong button? Sorry, this is not my normal clicker. So interaction. Interaction is actually handled by the main thread. I don't know why, but it is. No. There's lots of really important reasons why it's handled on the main thread, but it's really annoying. It's funny, actually, when I first started learning about performance, I was like, okay, I get it. Like, loading speed, rendering speed, this makes sense. Why the heck do we care about frame rate? Like, what does this have to do with anything? And this is why, is because it's all handled on the main thread along with all of those other like more obvious performance-y things. All right, our goal for interaction is, again, we want the response to our users to be immediate and we want it to be jank-free. So we don't want that like stuttering animation. We want, when they tap on a button, we want it to respond immediately. You know, so what causes this? There's 2 main things that we're going to talk about that cause a poor interaction experience. The first is input delay, and the second is dropped frames. So what is input delay? So all right, this is our timeline of what's happening. So we started showing something to the user here, right? So the user's like, oh, cool, I'm gonna tap that button. Oh, but wait, JavaScript file, our giant JavaScript file came back, and the main thread is in the middle of parsing and executing it. So what it does is it takes that tap event and it holds on to it for a while until the JavaScript is done, and then it will actually do something in response to what the user did. This is really annoying. I mean, we've all experienced this, right? So how do we prevent this from happening? Well, again, JavaScript. I have a love-hate relationship with JavaScript. And the main thing that we can do to make it better for our users is to ship less of it. We talked about code splitting a little bit earlier. Load only what you need to render, and then hold on and wait and lazy load all the rest of the JavaScript so that you free up more time on that main thread for it to handle user interaction. Another thing we can do is use the request idle callback, which unfortunately isn't implemented in every browser. But what that'll do is it'll allow us to chunk up our JavaScript and tell the browser, hey, you know, if the main thread is just chilling and doing nothing, go ahead and execute this JavaScript. But it's a lower priority than doing all of the more important things the main thread does. We can measure this. There's a polyfill that the Chrome developer team put out where you can measure your first input delay in your RUM metrics. And then total blocking time is a measure that's, it's new in Chrome, it's not implemented everywhere, but it'll tell you how long the main thread is blocked and can't respond to user interaction. And then finally, audit all of your frameworks, audit your third-party scripts. Make sure that if you're loading JavaScript in the browser that's gonna block your users from getting a response, that it's really, really important JavaScript to you. Like, do you really need to like execute that Google Tag Manager? Probably not. Although marketing will probably say, yes, you do need to. All right, moving on, animations. So going back to our friend 2.7 million pixels. So in order to have a natural animation frame rate that feels smooth to the user, we need to draw animation with 60 frames per second. So you can think of it as every single time we redraw what's visible in the browser window, we want to redraw that 60 times per second. So that means we have about 16.67 milliseconds to draw 2.7 million pixels, plus or minus that extra, like, they usually say actually to plan on only having 10 milliseconds to draw the entire screen every time you want to animate. So if you want to scroll, if you want to pop something open, it's really expensive. Oh God, I swear I'm like good at this. Okay. I'm never using this clicker again, Sergi. What are you trying to do to me here? Okay, so this is a new example. This actually is not what we were looking at before, but just to kind of show you what I mean by frame rate and dropping frames. Let's say that we have a button that when you click it, we use an ARIA controls tag to pop open a dialog that overlays over the entire screen. And because we are good citizens of the net and we want to enforce accessibility, our CSS only works to show and hide the overlay from display none to display block using our ARIA properties. And then we have a little bit of JavaScript that handles that click event and changes from ARIA hidden true to ARIA hidden false, and we go from display none to display block. So what does that look like? So we can think of this as being each of those little bars is a frame with 16.67 milliseconds in between for the browser to draw it. So when we click that button to open the overlay, we have to fire our JavaScript event handler. Ours was pretty quick. It probably actually wouldn't cause us to drop any frames. But during that period where where the JavaScript is executing, the browser can't redraw frames. So that's a dropped frame. That's a janky animation. Then that div style changes from display none to display block. Now, if you were paying attention, why is this bad? Well, when something is display none, it doesn't end up in the style tree. So the browser has to recalculate all of that style, and then it has to relayout, and then it has to repaint. Then it takes it and it recomposites on the GPU, which is like, hooray, great, we like that. We like the GPU. GPU is our friend. Reflow, however, is not our friend. So how can we fix this? Well, going back to our friend layers, layers are great because when we want to do things like animation, or if we want to do things like showing and hiding, when we use a layer, then the browser only has to repaint the layer that changed. Everything else stays the same. And then most of the animation is handled in the compositing stage. So you can think about, it's easier to take a layer and move it around relative to the background and then redo that math function than it is to have to redraw the entire thing over and over again. But again, be careful because layers are really expensive in memory. You don't want to create layers for no reason. You want to do it for things like this, where we want to have a smoother animating performance for our overlay appearing over the screen. So how can we do that? Well, we can change our dialog to use a CSS transition. In our case, we're using opacity. And then instead of using display none, we make it visibility hidden. So visibility hidden is in that style tree. It's still rendered by the browser. It just doesn't display it. So that instead of having to repaint the entire thing, it just switches that layer from the back to the front and then redoes all of that math on the GPU, and we drop way less frames as the user is scrolling. So the animation is way smoother. All right? All right, we're at the time. Are you ready to see the GIF? Okay. Allie knows how much I love this GIF. It just makes me crack up every time I look at it. All right. So I hope that we are all now feeling very much like our friend the cat here, and our minds are totally blown by how amazing web browsers are and the amount of crap that they do for us that we don't even realize that they're doing. So it's really easy to get super dialed into the code that you ship and forget about our poor, overworked friend, the browser. So I hope that coming out of this, we all have much more appreciation for all of the work that the browser does, and we're better equipped to make the browser happy so that our users can be happy by having a better experience. And again, how are we going to do that? Navigation phase, we want to get that over with as quickly as possible because that's opaque. Parsing, we want to get our DOM and our CSS into the browser as quickly as possible because that's what's going to allow us to move on to the all-important rendering step. Once we get to rendering, we want to make sure that we're doing as little work as humanly possible on that main thread, and we're doing more work on the GPU because the GPU is our best friend. And then finally, when we're thinking about users interacting, we want to make sure that we're providing instant feedback to their interactions and that we're having animations that are jank-free. And then we'll have a happy user and a happy browser. So this is the amazing link that I've talked about 100 times in the presentation. I highly suggest you go to it. And if you want to follow me on Twitter, I'm @kseiler. And thank you very much.
Okay, who is ready to start asking questions?
I have a question about the CSS modal, because the visibility still occupies space. So if you don't want it to occupy space, what is your recommendation for that?
So I'm sorry, I don't know if I pointed out or if I put it on the slide, but in order to make it really work, you have to also give it some kind of absolute or fixed positioning. And then generally, I find it's better to give it like a Z index that's behind the main content. But as long as it's visibility hidden, then it'll be in the tree and the browser won't have to relay out it.
So it's just paint.
Yeah, really, it's just layout. If it's in the tree, it doesn't have to lay out, it just paints it and then composites it.
Okay, I have a question. You guys can think all about yours while I'm asking mine. It's basically help for you to keep thinking. We did not talk much, obviously we don't have 15 or 20 hours, so
No.
About the network step, right? Like much, right? It was like 15 steps or something, like, still quite a lot, right? But I can imagine there is a problem with making 15 round trips. Can you quickly talk about why that is a problem and if there is any like simple things we can do to minimize that?
Yeah, so like obviously network conditions are variable, and the more round trips that we have to make, the more likelihood there is that there's going to be packet loss and that the browser is going to have to go back and re-request data because it didn't get a complete package. So some of the things that we can do to reduce that is, I think I mentioned them very briefly, but you can use preload and prefetch to say to the browser, okay, go off and make this DNS request earlier in the process. So like if for whatever reason, if we're hosting our JavaScript on a different server name than our main HTML file, then we say go off and prefetch the DNS request for this. So the browser, whenever it's idle, will go and do that early for you.
Google
and then
Google fonts.
Yes. Go watch Zach Leatherman talk about fonts. It's very important. And then another thing that we can do is preloading, which basically tells the browser, hey, I want you to go off and make a request for this thing like super early in the process because I promise you it's important. I'm not going to wait for you to go and find it. Another thing where that's important is with fonts, because typically when the browser is trying to decide if it wants to download a web font or not, it actually will go through creating the DOM and the CSS DOM and put them together and then look and say, oh, okay, we actually have an element that we need to render with this other font, and then it'll go off and request it. So if you use preload, you can tell the browser, hey, I promise you you're gonna want this font, go off and request it early. So like you can link rel preload in the head of the document. So those are some of the things that we can do to help the network process go faster. So there's a lot of performance stuff. It's overwhelming.
What are strategies when you have a website that has a lot more than 14 kilobytes worth of stuff for choosing and doing that well?
He works at Etsy with me. We have a lot more than 14 kilobytes. No, so I can't believe that I'm going to say this, but you can take the CSS for your above the fold content, which is kind of problematic to decide because what is the fold? Where do we decide to display content? Because the size of screens is completely variable. However, you can make your best guess about what CSS is going to power that content and then inline just that into your head. And then because it's inline, it will be available sooner, and then it can go off and make the request for the rest of your CSS. So like browsers are going to try their best. There's actually a ton of points early on where the browser will try to speculatively take half of the DOM and half of the it waits for all of the CSS DOM and it'll take half the DOM, and then it'll try to put it together and send stuff out earlier for you. So take whatever you can that is going to be for that above the fold content. And I hate saying above the fold. I spent like 10 years telling designers there is no fold. We don't know what the above the fold content is. But now it's like, oh yeah, let's load above the fold CSS. So anyways.
Hi. So you spoke about making browsers happy. What kind of browser makes you the happiest?
Ooh. I mean, I think that's a pretty easy question. Like as far as performance stuff, Chrome, like they put a lot of money and time and energy into making Chrome the fastest browser that they can. Firefox also is super awesome. I really like a lot of Firefox's privacy stuff that it does. But when it comes to sheer volume of like awesome new features, Chrome definitely wins.